Welcome to This Explainer. Today, we're going to take those tedious, headache-inducing math problems and transform them into a rapid-fire session of mathematical secrets. If you've ever stared down a massive number and just felt your brain freeze up, well, you're in exactly the right place. We are taking the boring textbook rules of squares and square roots and flipping them into instant mental hacks. Let's get right into it.
Okay, so think about this for a second. What is the unit digit of 5,278 squared? Would you really multiply a four-digit number by itself just to find the very last digit? Imagine sitting in an exam, sweating, trying to multiply 5,278 by 5,278. It would take literally minutes. And let's be honest, the chances of making a tiny calculation error along the way are incredibly high.
Which brings us to Section 1, Unit Digit Secrets. The golden rule here? Look at the tail. Seriously, you definitely shouldn't be doing all that manual math. Our first hack completely bypasses the heavy lifting by focusing solely on the tail end of the number. We call this the unit digit, and it absolutely holds the key to getting your answer instantly.
Check out the undeniable pattern of unit digits when you square the numbers 1 through 10. Just look at it. 1 squared ends in a 1. 2 squared ends in 4. 3 squared is 9. 4 squared is 16, so it ends in 6. 5 squared is 25, ending in 5. You get the idea. This exact sequence is basically the DNA of every single perfect square in existence. It's like a secret code hiding in plain sight. So, what does this all mean? The crucial takeaway here is that if you see a random number like 1,057 or 7,928, you instantly know they are not perfect squares. How? Because of their last digits. If a number ends in a 2, a 3, a 7, or an 8, you can completely rule it out. It is mathematically impossible for it to be a perfect square. But if it ends in a 0, 1, 4, 5, 6, or 9, well, then it has the potential to be 1. Now, let's apply this to our opening question. Watch how we can solve this in 3 seconds flat just by squaring the 8. We don't care about the 5, the 2, or the 7. Forget them. We only care about that final 8. 8 squared is 64. And what's the last digit of 64? It's a 4. So whenever you finally finish multiplying that giant number out the long way, I guarantee you, the last digit of your massive answer will absolutely be a 4. Boom, done.
Moving on to Section 2, the zero rule. Here, even is the magic word. Let's tackle those big, intimidating numbers filled with zeros. We all know that multiplying numbers with a ton of zeros can be tricky, mostly because it's so incredibly easy to lose track and miss one along the way.
But check this out. When you square a number like 400, which has 2 zeros, the amount of zeros in your answer perfectly doubles to 4. You simply square the non-zero digit, so 4 squared is 16, and then you just double your zero count. 2 zeros become 4 zeros. 3 zeros would become 6 zeros. It really is that ridiculously straightforward.
Because of this doubling effect, no matter how astronomically big the number is, a perfect square will always have an even number of zeros. So if you're staring down a multiple choice question and one of the options has 3 zeros at the end, like say 64,000, you instantly know it's a trap. It literally cannot be a perfect square because the zero count is odd.
All right, Section 3, Instant Calculation Hacks. Drop the pencil and use logic. Let's step away from the scratch paper entirely, because these next tricks, they're going to feel like pure mental magic. We're going to look at sequences and sums that usually force people to write out long, agonizing columns of numbers.
Like, imagine getting this on a test. How many non-squared numbers lie between 12 squared and 13 squared? Are you actually going to calculate 144 and 169 and then manually count every single number in between? 145, 146, 147. Honestly, you'd be sitting there forever. Plus, you might just miscount by 1 and get the whole question wrong anyway.
No way. You are going to use the 2n rule, treating the smaller base number as n. Whenever you're asked to find the amount of non-square numbers right between two consecutive squares, like 12 squared and 13 squared, or even 90 squared and 91 squared, you just grab that smaller base number, your n, and multiply it by 2. That's the whole trick.
So for our problem, you simply multiply 12 by 2, giving you an instant answer of 24 numbers. No counting required whatsoever. Between 144 and 169, there are precisely 24 natural non-square numbers. And the best part? It works every single time for any 2 consecutive squares.
Okay, how about this one? What's the sum of 1 plus 3 plus 5 plus 7 all the way up to 19? Do you slowly add up these first 10 consecutive odd numbers one by one? 1 plus 3 is 4, plus 5 is 9. Sure, you could do it, but what if the test asked you for the sum of the first 50 odd numbers?
Absolutely not. You just count how many odd numbers are in the sequence and square that amount. As long as the sequence starts at 1 and is completely consecutive with no skipped numbers, the math is incredibly elegant. If you have 5 odd numbers in a row, the sum is simply 5 squared, which is 25.
Since there are exactly 10 odd numbers in our list on screen, 10 squared gives us an instant sum of 100. If you had 20 consecutive odd numbers starting from 1, your sum would immediately be 400. You're basically transforming a tedious, boring addition problem into a 1-second multiplication trick. How cool is that?
Let's move to Section 4, Conquering Square Roots. Subtitle, Fixing Imperfect Numbers. We're going to see how all this logic builds when we're faced with numbers that aren't perfect squares, like 90 or 80. You see, sometimes exams don't just ask you to find a square root. They ask you how to fix a broken number so that it actually becomes a perfect square.
Now, this is the ultimate cheat sheet for knowing exactly which method to use based entirely on the wording of your problem. If a question asks what to multiply or divide by to make a perfect square, you must use prime factorization. But if the question asks what number to add or subtract, well, prime factorization won't help you there at all. You have to use the long division method.
Let's say you're asked what to multiply 90 by to make it perfect. We use prime factorization to spot the missing pairs. Think of perfect squares as a buddy system. Every prime factor needs a buddy, a pair. In 90, the 3's are a perfect pair, but the 2 and the 5, they're totally alone. To give them buddies, we need another 2 and another 5. 2 times 5 is 10. Multiply 90 by 10, and you get 900, a beautiful, perfect square.
But what if you're asked what to add to 80 to make it a perfect square? Here we use long division logic to find the closest squares. We know 8 squared is 64, which is below 80. The next square up is 9 squared, which is 81. Since we need to add to 80 to make it perfect, we just look at the gap between 80 and that next target of 81. We simply add 1. Easy, right?
Finally, Section 5, Geometry and the Triangle. We're bringing squares into the real world. Let's take all these square root secrets out of the textbook and apply them to actual shapes. Geometry heavily relies on our ability to quickly square numbers and find roots, particularly when we start looking at right-angled triangles.
The famous Pythagorean theorem is entirely built on our understanding of squares. It states that the longest side, the hypotenuse squared, is equal to the perpendicular side squared plus the base squared. If you can handle squares confidently in your head, this legendary theorem becomes an absolute breeze to solve.
Watch this. If we take our hacking rules and plug in the side lengths, we easily find the missing base of 4 centimeters. We take our hypotenuse of 5 and square it to get 25. We take our side of 3 and square it to get 9. We subtract that 9 from 25 to get 16. The final step? What is the square root of 16? It's exactly 4. Just like that, you've solved it.
It all boils down to this. You don't need to be a human calculator. You just need to know the secrets hidden in the numbers. Once you know the rules of units, doubling zeros, and recognizing consecutive odd sums, the math just does itself. You really don't have to calculate every single digit manually. You start treating math less like a chore and more like a puzzle, with an easy backdoor solution.
So I'm going to leave you with this final test of your new hacking skills. If a right triangle has a perpendicular side of 6 centimeters and a base of 8 centimeters, what is the length of its hypotenuse? Can you solve this triangle in your head before this explainer ends? Take the 6, square it. Take the 8, square it. Add them up and find the root. Remember, it's all about the squares. Thanks for joining me on this deep dive, and keep hacking those numbers.